We'll be solving LeetCode's problem number 207, which is called course schedule. It's a medium difficulty problem, and to solve this problem we'll be using an approach called Topological Sort, or more specifically Kant's algorithm, which is a BFS or breadth-first search based approach. And if you're unfamiliar with how BFS approach works, I suggest you checking out my previous video, but even without it I think you will be able to follow this video easily. Let's quickly read the description of the problem. So there are a total of num courses you have to take, labeled from 0 to num courses -1, and you're given an array prerequisites where prerequisites of I is a pair AB, where indicates that you must take course B first if you want to take course A. For instance, the pair 0, 1 indicates that to take course 0 you have to first take course 1. Return true if you can finish all courses, otherwise return false. So let's go through these examples. So in the first example, number of courses is 2, labeled 0 and 1, and prerequisites array contains only one pair, which is a pair 1, 0, meaning that 0 is a prerequisite for 1. In this case, the output should be true, because there is at least one valid solution or valid order of courses where you can complete all courses, or both courses in this case, for respecting the prerequisites which are given here. That order is you first have to take course 0, and then you can take course 1, because 1 has a prerequisite course 0. So yeah, in order to take course 1 you need to take course 0 first. So it's possible, and that's why the output should be true in this case. On the other hand, the example 2, we again have two courses, but here there are two pairs in the prerequisites array. One is 1, 0, meaning that 0 is a prerequisite for 1, and the other one is a pair 0, 1, meaning that 1 is a prerequisite for 0. In this case, the output should be false, because it's not possible to complete both courses by respecting these prerequisites listed here. So if you take course 1 first, you will break the first rule, because 0 is a prerequisite for 1, so you need to take 0 first. But at the same time, if you take 0 first, you will break the second rule or second prerequisite pair, meaning which says that 0 course to be taken, you first need to complete course 1. But technically it's like a cycle between these two courses, and because of that there is no valid order of the courses in which you can complete all courses and at the same time respect all of these rules listed here. Before we discuss the actual solution of the problem, let's quickly go through the constraints. So the number of courses is an integer between 1 and 2000. So it means that we can assume that there will be no 0 courses provided as an input parameter, or a negative number. Prerequisite.length is a number between 0 and 5000, meaning that there could be that prerequisite array can be empty, meaning that there are none of the courses has a prerequisite. And prerequisites of I for any given I.length is 2, meaning that every item in this prerequisites array is basically a pair. And also for every pair AB in the prerequisites array, the values A and B are between 0 and number of courses, strictly less than number of courses, because they need to represent the courses which are labeled with numbers from 0 to number of courses -1. Hence we have this rule here, or constraint. All the pairs in the prerequisites array are unique. Okay, let's see how we can solve this problem. So first of all, to solve this kind of problems where you have a list of some courses or another and there are prerequisites, which is the case here. But another relatively similar problem would be, imagine that you are building a package, like a software package, which has dependencies. So it depends on some other packages which are used by that main package. But those other dependencies can have their own set of dependencies. And in order to build a package, you need to build all of its dependencies. In order to build all of its dependencies, you need to build their dependencies too. So basically we can imagine that as a tree, dependency tree, let's call it dependency tree, and imagine that your task is to find a valid order of dependencies in which they have to be built in order to build your package. So similarly here we have courses, and we need to take all of those courses, but we can't take them in any order, because some courses have prerequisites. So we need to take the prerequisites first and then to complete those courses. And that kind of problems are problems that can be solved using an approach which is called topological sort. And there are multiple algorithms that can be used to implement this approach, and one of them is Kahn's algorithm, which is BFS based. BFS based means that it's breadth first search based problem. If you're unfamiliar with how BFS approach works, I suggest you to checking out my previous video where I solved another problem using this approach. But anyway, I think it will be quite straightforward for you to follow this video even if you are unfamiliar with BFS. So maybe this video is also another way to learn how this approach works. So first of all, when we are given two parameters, so we have to implement this method called canFinish, which takes number of courses integer and this array of pairs, which is called prerequisites. So how we can imagine these courses and their relationship, which is provided in with this prerequisites array? Well, we can imagine these courses as a graph, where every node of the graph would be a course, and these prerequisites actually model the edges of the graph. So let's say that A is a prerequisite, course A is a prerequisite for the course B, that there will be a directed edge from A to B. And if there is a valid solution to this problem, that graph has to be a cyclic directed graph, or DAG. I'll edit here. What does it mean, directly acyclic graph? Directed means that all the edges are directed. So if there is an edge from A to B, that edge is directed from A to B. It doesn't mean that there is an edge from B to A. And acyclic means that there are no cycles in the graph. So if we take this graph as an example, here I downloaded this image from the Wikipedia article called Directed Acyclic Graph. So here we have a directed acyclic graph. Why directed? Because every edge is directed from one node to another. Remember that if there is an edge from A to B, there could be a directed edge from B to A too, but it would be another edge. So those would be basically two edges. Unlike so when a graph is directed, that means that its edges are directed. At the same time, this graph has no cycles, meaning that if we take any path from A through any other node, we won't be able to return back to the same node A. And that applies to every single node here. If we start from C and let's say we take this edge and then we take this edge, but there is no way to come back to the node C. So that means that this graph is DAG, or directly acyclic graph. And if these were courses, A, B, C, D, and E, and these edges were prerequisites, so there is an edge from A to D, meaning that A is a prerequisite for D, this graph would represent the courses and prerequisites. So, and if this graph is DAG, that means that there is a valid solution. And here there are, I think, at least two valid solutions. One is to take course A first, then courses B and C in any order, because when A is completed, then we can complete C and B. We can take C first and then B. And when B and C are done, we can take course D. And when D is done, C is also done, A is done, then we can complete course E. So there are two valid solutions, if I'm not mistaken. One is A, B, C, D, E, and the other another solution is A, C, B, D, E. So we can take the courses in that order. And in this case, if in this case the output should be true, because we can finish all courses. On the other hand, if there was a cycle, let's say from C to A, we won't be able to complete all courses, because if we take A first, C cannot be taken, because second, because if there was an edge from C to A, if we take A first, we cannot do it because C is a prerequisite for A, and vice versa. If we take C first, we cannot, because A is a prerequisite for C, and that's why the outcome in that case would be false. So how Khan's algorithm work? So first we need to convert these input parameters to the graph, like structure. So basically to the directed graph, where nodes will be the courses. So given that nodes are labeled from 0 to number of courses minus 1, labels would be 0, 1, 2, 3, let's say. 0, 1, 2, 3, and 4, for instance. And edges will be, if there is a prerequisite called BA, let's say there is a prerequisite BA, then there will be an edge from A to B, like here. Okay? So, like, the very first thing we need to do is to convert these input parameters into to a directed graph. Then, once we've done this, how does the Khan's algorithm work? First, it takes all the nodes that has no inbound edges. So it would take all the nodes which has no prerequisites. Here it's only node A, or we can say every node, the number of edges that goes into a node is called in degree. So we need to take all the nodes with in degree equals 0. Here it's only node A, and that will be the first node that will be, or the first course that will be taken. Once we are done with that, we will edit we will remove it basically from the remove it from the graph, and we will update, basically remove all the arrays that goes from the removed node A. And then some new nodes with in degree 0 will appear. So node B and C. So if you remove A, these two arrays would be removed, and then B and C would become nodes with inbound in degree 0, and then they can be taken next in any order. We can take B or we can take C first, doesn't matter, but let's say we take B first, then we will again remove the arrays that goes from B, and so on and so on. How we can implement this in code? Well, we will create the graph, but at the same time we will create a separate structure, an array, which will be called in degree array, and which will keep track the in degrees for every node, and it will be updated as we proceed with the algorithm. So that in degree array will have the length of number of courses. Well, where in degree array of I would represent the in degree of the node I. So it will be way simpler to understand this approach when we switch to the code. And before we switch to the code, let me just mention one more thing. So first thing is that I wanted to clarify one more time is the problem, the method should return true or false whether there is a valid solution or not. But if there is a valid solution, there could be multiple valid solutions. That's something which is important to notice. But in our case, we just need to return true if there is at least one valid solution. So as we proceed with this algorithm, let's say we take node A first, we will use a queue and we will add it to the queue, and while that queue is not empty, we will take nodes from the queue. Technically it can be in any order, but we can use queue which follows the first in first out approach, and we will add those nodes to a result list, which will basically keep track of the order of the final result. Given that we don't need to find the order of a valid solution, we just need to return true or false. The final outcome would be whether that result list contains all of the nodes, all of the courses. If yes, then we have a valid solution, then we return true. Otherwise, if it does not contain all the courses, it would simply return false. So that's how we are going to check the final outcome of the problem. So let's quickly try to implement this solution. So in this case, I'm going to assume that all of the constraints that I mentioned earlier are satisfied. But if you are given this problem during an interview, please do clarify with the interviewer whether you need to take care of the input parameters. We can ask whether we can assume that the input parameters or the constraints are satisfied, and if not, we would need to add some extra checks. For instance, whether this is a negative or zero number or zero, whether these edges are unique, and things like that. But here we are assuming that that the input parameters, the constraints are satisfied, and we are not going to deal with them, just for the sake of simplicity. Okay, so like the very first thing we need to do is we need to create the graph and in degree array. So to create a graph, I'll be using a hash map integer list of integers is equal to new hash map. So I'm using Java programming language, but yeah, it should be quite straightforward to convert this code to any other language. Why integer, list of integer? Well, integer, the key of the map will be a node, and the value of the for the key will be a list of nodes that are adjacent to this node. So here, for the map of A, will contain a list of 4 nodes B, D, C, and E, because there is a direct edge from A to all other nodes. Okay, and let's initialize the in-degree. Let's create the in-degree array. So it's gonna be an integer array in degree, which will have, num courses, which will have the length of number courses, where in degree of I represents the in degree of the node I, or of the course I. In Java, when you do something like this, it will allocate number of courses integer values, and by default all of them will have the value of 0. So we don't need to initialize this array with zeros, because it's already in Java, it's already initialized. So let's quickly create the graph. So what we need to do, let's go through the prerequisite. For each edge in prerequisites, we can say int from course is edge of 1, because by reading from the description, it says pair 0, 1 indicates that the 1 is a prerequisite for 0, and that in our graph it will be an array from node 1 to 0 in this direction. I think if you switch the orders, it would still be fine, but yeah, let's stick to this description here and to the way how I explain this, and I'll say that from node is the second value in the pair, and int to node is the first value in the pair. Okay, and so what we need to do here, we need to add this. So we need to say something like this: graph of from is equal to list of 2, something like this. But in Java, I could do this check. I can say if graph contains key from, if it does not contain this key, I can initialize it with an empty list. I can say graph dot put from new array list, and then I can say graph dot get from add to, something like this. But this takes 3 lines, and luckily in Java the map interface contains a better method which is called compute if absent. So I can say, and I can do all of these things in one line. So I can say graph.compute if absent for the key from, and the second parameter, it will be a function which basically creates a new array list, and then I can add the value to that array list. So basically it's the same thing as the code I wrote previously, but it takes it's kind of a more elegant way of writing the code, so it's up to you how you want to implement it. And additionally, what we need to do, we need to increase the in degree for the to node, because there is an edge from the node denoted with from variable to node denoted with to variable, and that's why we need to increment the in degree for this node. Okay, so we can say something like in degree of 2 plus plus. Okay, now we are done with this initial with the graph creation and this in degree array. Now we need to implement the solution, the rest of the solution. So we need a queue of integers. In Java, the linked list is an implementation of the queue interface, but it's just a simple queue. And what we need to do, we need to put or add to the queue all the nodes where in degree for which the in degree value is 0. And those nodes we will start, we are taking the courses, we will take those courses first, because that means that those courses have no prerequisites and we can take them first in any order. So we can iterate through the nodes for int I equals 0 while I is less than in degree dot length, or while I is less than number of courses, it's the same, I plus plus. And we can say if in degree of I is equal to 0, we can say we will add node I to the queue. To add a value to the queue, we can use both methods offer or add. There are some differences which are not important for this for this problem, so I want to talk about them. I won't spend much time on it, so we can use offer, for instance, and we will add node I to the queue. So now when we have initialized the queue, let's implement the last part basically of the solution. And also we will be needing a list of integer result where we will be adding the nodes as we go through the graph, and the order of the nodes in this result will represent the order of the courses in the final solution if there is a valid solution. That means that at the end of this problem, this result list will contain all the nodes in a specific order, and if it contains all the nodes, that means that there is a valid solution. Otherwise, it will contain a subset of the courses, a subset of the nodes, and in that case the solution, there will be no solution, and the outcome will be false. So we can say at the end return result.size is equal to number of courses. So if the result.size in the end is equal to the number of courses, that means that all of the courses are added to the result and there is a valid solution. And if you are interested in the order of a valid solution, then you can just simply iterate through this list. And let's implement the solution. So while queue is not empty, we will take node let's call it int course is equal to q dot poll. Poll will take a value from the queue which was added first, and we will add this course to the final result dot add course. Okay, and finally, when we took a node from the queue, we need to update the inbound array. So basically, let's say that this was the graph. We have taken A from the queue, and now we need to update the inbound array for all nodes or courses for which A was a prerequisite. So in this case, it will be all other nodes, because there is an array from A to every other node. So how can we do this? Well, we can search in the map. So we can say for each integer, let's say course next in the graph.get course, this course which is taken out. But the problem is, if this course is not a prerequisite for any other course, then this will be null, because this course will never be added to the graph, right? So we are risking a null pointer exception basically here. So instead we need something like this: graph.get or default course new array list. Do I have too many parentheses? Yeah, something like that. So if course is not present in the graph, then we will return an empty list. This way we are just avoiding a null pointer exception. For each integer next in this array list, we need to decrease the degree value for it. So we need to say in degree of next minus minus. Additionally, in degree was 1 at the beginning for B. After removing A from the queue, in degree for B becomes 0. And that means that this B can be taken next, so we need to add it to the queue B. For C, it was also 1 before. When we removed A from the queue, in degree for C becomes 0 too, so we will be adding C to the queue as well. And for D, it was 3 at the beginning. After removing A, it will become 2, but given that it's still not 0, we are not adding it to the queue. So we need to check here if in degree of next is 0, we add it to the queue, queue.offer next. And this is it. Maybe we can simplify this a bit. If minus minus of next is 0, we can write it this way, but basically it should be the same. And this is it. This would be the solution of this problem. Let me simply zoom it out so you can see the whole solution. Okay, let's let's test this out. So let's say something like this. So this solution is placed in the method called canFinish within the class solution. So we need to initialize the solution object, solution equal new solution, and let's say that int num courses is 2 and int prerequisites is a new int of, I think it's 0, 1, right? Let's use the same example from here. It's 1, 0, okay? But it doesn't matter. In both cases, the solution should be true, right? And let's say system.println result is solution dot canFinish num courses prerequisites. We have, okay, we ended up in an infinity loop, so we have a problem here. So let's go and try to debug the solution. Sorry. Okay, so let's quickly go. Okay, ground in degree, and let's see what do we have here. So in degree of 0 is 0, of 1 is 1, which is expected, right? Because 1 is a prerequisite. Let me see here. 0 is a prerequisite for 1, so there should be an edge from 0 to 1, and that's why, okay, this is fine so far. And okay, in the queue, okay, here, okay, we added to the queue 0, which is fine, and we haven't added 1, which is also fine. And then while queue is not empty, queue wall, so we have taken 0. We have taken actually 0. Yes, this is fine. Oh, okay, sorry, I made a huge mistake here. We cannot do something like this because this will, okay, this doesn't, okay, this is incorrect. So if degree in degree of, okay, this is simply incorrect. Apologies. So what we need to do for each next, oh, actually, why is it incorrect? Oh, in degree, okay, we need to in degree of next, we need to, okay, this was just a big mistake. So for the next, we need to decrement the in degree, and then if we have reached to 0, we can add it back to the queue. So yeah, that simplification that I mentioned was was just incorrect. Okay, let's try this one, and here the result is true. Okay, but if we add, basically if we create a cycle here, the output should be false, and it is false. Why is it false? Because it's not possible to complete both courses 1 and 0 in this particular case, because there is a cycle. So 1 is a prerequisite for 0 and 0 is a prerequisite for 1. So this seems to be correct. And also let's add a breakpoint here. I'll remove it from here. Actually, I can do it here as well. What I wanted to say, to show you, so if you are interested in a valid solution, here the result will keep track of a valid solution. So result, okay, in this case is 0 because there is no valid solution. But if I remove this, okay, something like this, so here the result is true, and if we open the result, it contains 2 nodes, and the order of them basically tells us in which order we should take the courses to complete them all. So we need to take course 0 first, followed by the course 1. So if the problem statement is, instead of returning true false answer, to return a particular order, then you should just print the order from the result list, and it will be a single valid order. But as I said, there could be multiple valid solutions. And before we finish, let's just quickly discuss the time complexity of this problem. So the time complexity of this problem, or general time complexity of the Kahn's algorithm, is big O of V plus E, where V is the number of nodes in the graph and E is the number of edges. Why is it V plus E? So let's go step by step. So here we build the queue. Here prerequisites, the length of the prerequisites is actually is equal to E. So we can say here that E is a prerequisite. So prerequisites, the number of elements in the prerequisites is the number of the edges in the node. So here we iterate through the prerequisites, and the total number of iteration is equal to the number of edges of the graph. And here what we do, this takes constant time, this line here. So here we have the number of edges time complexity for this part. Then here what we do, we initialize the queue with the certain nodes, and this queue, if the graph is DAG, directly acyclic graph, will have the number of nodes in the worst case, or in every basically case, it will have this part will have this graph will be populated with all nodes at the end. So it will contain all nodes, and at every step we take one node from the queue, and then we iterate through all edges of that particular node. Once we are done with this node, we take another and go through the edges of that other node. So some may say, okay, here we have n nodes or v nodes, whatever, and for in every step we can potentially iterate through all edges, but that's simply not true, because at every step we are eliminating a certain number of edges and we never go back to them. So in total, in every step we will iterate through a subset of edges, and the total number of edges through the whole while loop will be equal to the number of edges, meaning that here we have v iterations. So that's why the total time complexity is equal to v plus e and not v times e. And that's basically the time complexity of the Kahn's algorithm in general, and the overall time complexity of this solution. So that will be it for this video. I hope that you liked it, and yeah, I'll see you in the next video where we will be solving another problem using this Kahn's algorithm, but it's gonna be a hard LeetCode problem. Thank you.